2 years, more than 2 years actually. It has been a long journey so far. What I'm going to present you here today are some of my experiences with RxSwift. I'm hoping that maybe you'll have some good use of them. We will learn quite a lot during those 2 years. So, arrows. Usually, when I try to solve some problem, there is rarely an exact solution. So, what you try to do as a start, can you maybe turn the volume a bit down? What I try to do is I try to figure out what are the arrows. So either the arrows point in the direction of your solution or they don't. So what I'm going to do is try to construct those arrows for you today. And if you have the same origin, say starting point as I did, and those arrows are valid for you, maybe you'll end up in the same place that I did. Okay, so just in case you haven't seen any RxSwift code, it looks something like this, and I'm going to try to convince you to model your systems and write your code in this way. It looks a bit weird at start, but trust me, it's worth it. Okay, so I have a confession to make. I'm really, really lazy. So if you're lazy, you can raise your hand. No? Yes? Okay. Yeah, I'm really lazy. So that's kind of my first confession. My second confession is that I really enjoy deleting code. There is nothing that gives me more joy than deleting code. Why? Well, you usually can delete the entire feature just because you don't like it. But what you can do is figure out how to do it more elegantly, how to do it in a more concise way. So that's what actually gives me pleasure is, solving problems in an elegant way and writing really short, concise code. So if you really can decide, what goes into your app, and the feature is the same, the only thing you can figure out is how to reuse some other code that maybe you wrote some time ago, maybe your coworkers worked on it, and write it completely, or maybe it's somewhere on GitHub. So for you to be able to do that, the code has to have certain properties. And the property I'm talking about here today is composition. That's the secret juice of Rx. So when somebody says composition, immediately this comes to my mind, like pure functions, right? Pure functions are the jewel of composition. They're really easily composable. You can unit test them. It's really hard to mess up a pure function. But there are problems with this approach. Not all systems can be modeled using pure functions, right? There is this class of systems that are called, I would say, reactive systems. And they're basically like UI, network calls, input, output, timers, asynchronous operations. And you can't actually model them as pure functions. So what do you do then? You try to figure out, maybe there's some simple way how we can reason about them. So I would really want to explain one thing first that I think is really important. And that is the word reactive. That has been quite a buzzword lately, and a lot of people assume what it means. What it means to me is basically, it's a property of your system. You can choose, do you want to do reactive programming or not? Your applications, if you work with UI, their reactive properties need to be handled in some way. So you can either choose to manually do like target action, manually do mapping, combining results and binding to UI, or you can use some more automatic solution. Okay, so what do all of these kind of reactive systems have in common? How can we tackle this problem in a systematic way? Well, what they all have in common is they all work with callbacks. They all have an interface that takes callbacks. If you are working with timer, then you need to know when the timer will take. If you are working with some buttons, then you need to know when the user will tap on screen. And you can actually go through these examples one by one, and you recognize there is a callback in each and every one of them. Okay, so now we have actually made our original problem equivalent to a problem of how do you compose callbacks in a generic way. So, this is kind of generic callback interface. It doesn't have any special assumptions. What it does is it takes a callback, so here is a callback. You can send any kind of message through that callback, and it returns something called disposable. I will explain what does disposable mean a bit later, okay? But this is pretty generic, universal callback interface. Okay, if you take a look at our Swift repository, you'll notice that that interface is a bit different. It has an event. So why does it have an event? Well, people who have worked on the original RX implementation, they noticed that there is a certain set of control signals that you need to handle in almost all of these systems. For example, you need a generic way, how do you communicate that an error has occurred. So that's why, like, this is how it looks like. It has an error case that enables you to report in a generic way that your producer has an error out, and it won't actually send any more elements. It also has a completed event, and that event actually kind of signals that your producer has completed producing elements, and that's it. You won't receive any next elements. But the reason why those exist is to make your life simpler. It isn't any special assumption about the original producer. So these two interfaces are pretty much equivalent. We don't lose any generality there. And this is how disposable interface actually looks like. It's a bit different in the repo, but it basically comes down to this. Okay, so we've explained what is like the basic interface in RX, but we haven't explained why is this actually a sequence. Why do we keep calling it observable sequences? What are all these sequences we're talking about? So it all comes down to explaining what happens after subscribe is called. So after subscribe is called, some private resource is created. For example, if you're creating a network call, then an HTTP connection is being initialized. You already have an observer from the outside. You pass that observer to that private resource, and you get back a subscription. Okay? And what comes later is you actually, start producing some messages. And a sequence of those messages, a sequence of calling that callback are actually the observable sequences we are talking about here. So there is a really common analogy that people use when they try to explain what RX is, and when they try to explain this process. And that analogy goes something like this. You have a tap of water, and you're observing a water dripping from that tap of water. Each drop of water is one element of an observable sequence. And this is how you get the elements. So what this is, the subscription, it's a valve. When you want to stop the water from flowing, you close the valve, and you stop water from flowing. And that is approximately how RX works, but there are two crucial differences that you need to understand. Well, the first one is, after you call subscribe, there wasn't any tap of water before. It is synthesized out of thin air. It is materialized right in front of you. The other crucial difference is that once you actually close the valve and stop elements from flowing from that water tap, you destroy the water tap. So after that, there is no water tap. So it might seem a little subtle, but I'm going to explain why this is important. This is important because what happens when you call subscribe twice? Naive assumption would be you have a tap of water, you're observing it once from one side, you're observing it another time from the other side, you have one tap of water, you have one resource, you're only observing the element. But what actually happens by default is that you are materializing two water taps. If you are calling subscribe 3 times, then you are creating 3 water taps. And if you call this pose on the one subscription object, it doesn't have any effects on the other water taps. Okay, so that is a crucial difference to note. And you can, of course, make Rx work like there is a single water tap by using some special operators, but that is not the default behavior. You need to make it to work that way. And there are valid reasons why this is the case. Okay, so maybe let's with some simple examples. The reason why I'm actually showing you code and not presenting in some playground is because I had really bad experiences with presenting Rx inside playgrounds. So I'm sorry. Screenshots we'll just have to do. But you have a playground in the Rx repository with all of these operators. You can check them out, see how they work. It's pretty simple. Okay, so this is an empty sequence. What it does, after you call subscribe on it, it will produce a single event, and that is completed. Like, this is a pretty simple case, right? Okay, so you can also create a sequence of one element. In this case, that element is string, and its content is hello Rx. Okay, after you call subscribe, you have 2 messages. One next, and one completed that will try to communicate, okay, I'm done, there are no more elements. Okay, then you can create a sequence of 2 elements. It will work the same. You get the first one, then you get kind of waving hand emoji, and then you get the completed. Okay, so this is maybe a bit more interesting. This is the first time we have a side effect. So this will create some kind of internal timer that every 1 second will produce an element, and you can see an array of elements, basically a sequence of elements. It will go 0, 1, 2, 3, 4, and that way indefinitely. So you can play around with it a bit. So you can create one sequence of letters, one sequence of numbers. You can combine the latest value in each of the sequences, and you can create a sequence of tuples. So you can see that it's easy to play around with this and to add more behaviors, and then sooner or later you'll come to some code like this. This is a pretty standard kind of autocomplete code. So what is cool about this code? Well, you can do this kind of dot pattern for as long as you like. We have really tons of operators. It's kind of fun. No problem there. So what this means is basically that your code is composable. I can just select like these middle 3 lines, these 3 dots. I can just copy paste them into some other extension method. It's in really heaven for refactoring. It's just brainless refactoring. You just copy paste it and it will work. It will always work. So the one thing that actually enables all of this is a property called closure. So there is a language called closure. I'm not talking about that. When usually you say closure, people think about lambda. So I'm not talking about lambdas. Closure, it's a kind of mathematical term. What it means is if you have some set of objects and you have an operators and you apply certain operators, you get an object from this set. In this case, we have an observable sequence. You can apply really a bunch of operators, and as a result, you'll get an observable sequence. So this is kind of the juice that actually powers Rx, and why this is so cool. This is what enables you all of these great properties I was telling you about. at the beginning. Your coworker can write your code, somebody at GitHub can write your code, and you can easily reuse that code in a new environment. You can take this code, you can put it inside a unit test, and you can easily test this code. So it really has all of these nice properties, and they all kind of are all follow from the disclosure property. Okay, but there is kind of one thing to note. Once you call subscribe, you don't get, as a result, an observable sequence. So you're kind of leaving that set of observable sequences, and you get something that's called subscription. So subscribe, every time you call subscribe somewhere, it hurts compositional properties of your system. So this is the reason why you shouldn't really try to subscribe unless you really need to. You should try applying the operators, maybe creating your own operators, but not subscribing to observable sequence, because once you do that, that kind of breaks the original party and magic. But it kind of gets worse, because people write code like this. So this is, again, pyramid of doom. So, like I've explained to you, callbacks are equivalent to observable sequences, but that also kind of backfires because observable sequences are equivalent to callbacks. So this is kind of using Rx in reverse as a kind of callback engine or something. Usually when you see code like this, it is pretty trivial how to get out of this pyramid. So I can tell you that if you do this, just brainlessly and don't think about anything, just use flat map latest, you'll get it right in probably 99% of cases. So this is really practical advice. Okay, so what does Rx do for your reactive systems? We can't change the nature of the problems you're solving, but we can kind of heal your systems. We can take all of these other parts out of your systems, like we can take mutations, we can take locking, concurrency, we can take all of these control state machines, error propagations, things that you really don't care about, and put it in one place, and that is the Rx Swift code base. So I'm probably a maintainer of the ugliest code base in the world because of this, but somebody has to do it. Ugly code has to live somewhere. And yes, it's not really an easy job to maintain it. But that leaves you with a really awesome premise. You can write pure functions in your code, and you can use those pure functions to modify the system, to modify these operators I've showed you earlier. Okay, so one thing people usually say is that Rx has a steep learning curve. And that can be the case. I'm not saying that everybody understands the concept immediately, but it doesn't have to be a really steep learning curve. Probably the one thing that's confusing to people is that when they see Rx code, they see all of these operators, and they think, oh my god, how many patterns are they? Do I need to learn all of them? I can't understand anything that's on the screen. That's really not the case. You maybe have 10 or 15 operators, so it's really, really small. Like in my everyday work, I probably don't use more than 15 operators, if that much. And I really know that you don't have to learn a lot because I have a horrible memory. Like I have like probably one of the worst memories of the people you've met. And I really don't have a lot of problems using it. If there is some exotic operator that I don't use all the time, I would maybe look it up and see, is this something I really need to do? But usually it's pretty simple. The interface is small. I've presented you the interface just a couple of minutes ago. It's maybe a little weird at start, but maybe try to play with it. It's really not that hard. Okay. So what I really want to demonstrate in this first part of this presentation is I wanted to construct arrows that kind of point towards Rx. everybody wants a composable way to model their reactive systems, and Rx has really awesome compositional properties. Practically all reactive systems are based on callbacks, and callbacks are equivalent to Rx. If you have callbacks, it's pretty trivial to wrap them, and if you have Rx, as I've demonstrated, it's easy to use them as callbacks, but please don't use them. There are probably a lot better ways how you can use it. Okay, so I could probably talk all day about a lot of interesting topics here. I'm not. It would probably be a really boring presentation. But there is a lot of nice properties that Rx has, and they all kind of follow from that simple model of observable sequence. What I would really want to do is maybe let's try to explain, how to build some more complex reactive systems out of it. So usually there are some challenges that people face when they start with Rx. I also had the same challenges. It's perfectly normal. It's a little unusual concept to start with. But first question is, these observable sequences, like, what do they represent? What are the semantics? Are they kind of events? Are they used to synchronize state? How should I model my systems? Another problem is I have like this huge legacy app. How do I integrate Rx with it? Will it work? Do I need to change my entire application to use it? The answer is no. You can introduce it partially, and I'm going to demonstrate a bit later how you can do that. Actually, we have a pretty big legacy application, and we are introducing it in a partial way. So, how to do architecture with Rx? What I mean by this, how do you manage state? Because if you have state, then you need to figure out where to put that state. Where does that state live? Rx is by definition more stateless concept. It has some internal state, but it doesn't really say where should your state live. There are also questions like how do you introduce Rx to new team members? That's such a steep learning curve. And how do I educate them to use it in a good way? We had some of these challenges, and I think I'll demonstrate a bit later how to overcome them. So, how do you do code reviews? Because everybody using Rx has their own way how they can solve problems. And we also, have some ideas how to make this better. And, is there some normal way how we can model all of Rx solutions? And all of these questions, we were actually facing them. I work at a company called Velabit right now, and we are using Rx. And what we actually figured out that there is a pretty simple solution for all of these problems. And it's something like this. So you have state. That state has to live somewhere, right? You need to have state in your app, otherwise you'll always present an empty screen. So how do you model your effects? What I mean by effects? Like, how do you model your UI? How do you model your network communication? How do you model Bluetooth communication, your timers? Actually, how does that app run? How does it become from a state into a product you can ship to the App Store? Well, all of these side effects, they need to depend on something. And in this model, basically, the only thing that they can depend is some state. So that's this part. These are side effects. Side effects are these loops. And after you do some side effects and communicate with the external world, well, you need to potentially write the results somewhere so they can be stored. And since you only have state, then the only place where you can store them is inside that state. And that looks, if Rx was weird, maybe this looks really, really weird. Like, how can this thing work? Because it doesn't even have an input. Like, what is the input to the system? Well, the input to the system is a feedback loop that just ignores the output state. So it's pretty simple how you can introduce some external input to this system. So I'm going to just present a screen with a lot of the arrows that actually led us to that solution called RX feedback. So scan operator, it's a standard operator. It's already there in all of the RX implementations. So that's the thing. CQRS, command query responsibility segregation. It's a concept that has been out there for quite a long time. And you can practically prove that if you are doing something like that, you'll probably end up with code duplication somewhere. So the Elm architecture, if you ever heard of Elm, is pretty similar to RX feedback. The difference is that they do effect in a slightly different way. So instead of observing the state, they emit some kind of value type. But basically, conceptually, it's really, really close. You've probably heard of unidirectional architecture. These loops, it's a little hard to notice, but they're actually unidirectional. If you take a look at the loop at any point, it's pretty straight. Once you zoom out, it's kind of curved, but it's really unidirectional. What we also wanted to do is we wanted to write cross-platform code. And we wanted to decouple real business logic so we can cross-compile it in different platforms from the effects layer. So that architecture is really also awesome to do that. There are also a bunch of kind of similar architectures out there on GitHub. One of the guys that was active at RX community wrote ReactorKit. Databases in general. I mean, you have this huge bag of mutable state. It's pretty good thing. And the databases have worked for us in the 70s. Event sourcing goes pretty well with this architecture. There are some server-side solutions that are also kind of similar to this. Guys from Netflix have now Redux observable. And Redux is basically that center part, the reducer and the state. Okay, so how is this thing implemented? We have an operator, right? So you can use it as an operator inside RX. It takes a state, it takes a transition table, and it takes a list of feedback loops. And that's pretty much it. You can also use it as an architecture. If your state is really huge, then you wouldn't use an operator, for example. If you're modeling the entire app, then your state is inside the databases and you actually model the feedback loops manually. We are also doing this at the current company, and it worked really awesome. I've just put an implementation here. You don't need to understand what it is. I just wanted to point out that it's really small amount of code. It's nothing like how do you implement this operator is really complex, something. Okay, I have a demo. Basically, on a plane to here, I think it's probably mandatory for conference speakers to write to-do apps in the plane. So I've done the same. I've written a kind of to-do app that I'm going to present you today. I've also pushed this to-do app to RX feedback repository, so in case you're curious, you want to check it out, you can see the latest version there. And this is actually, okay, so we have a simple to-do app, but I've made it a bit more interesting. Instead of just making a to-do app, if you see those kind of check marks and bird marks, what it actually does is to synchronize that to-do list with some server, with some external storage. So it's pretty simple. You can add a new task, blah, blah, blah. And maybe I'll make it a bit smaller. Okay. It's down there. You can delete tasks. Nothing really too interesting here. And that's mostly it. And when you click on some task, it's being marked as completed and it's being synchronized with the server. So what does this burn mark mean? That means that the synchronization server has failed and we'll need to do retry at some later stage. The check mark means that, yeah, we have synchronized the data with some external service. Okay, so let me try to show you code for this, kind of a quick review. So it's not so important what is the exact code. What is important is how much of code there is or how small the code is. So this is the state. It's like 45 lines. And this is the reducer. It's also about 10 lines or so. So this is really all that it takes to understand business logic at its high level. To understand what are the states of the system, where it can be, how does it get into that state. So if you have a new developer, all it has to do is find the part where the system is defined. Okay, so the next thing is, how do you figure out what are the effects? Well, here are the effects. It's pretty simple. We do a dependency injection. So what you have here is when you initialize the system, you give it initial state, you give it a UI feedback loop that we have constructed from the outside, and you give it a synchronized task. That is an anonymous function that is being passed from the outside as a dependency, and that's the exact kind of process that we are using currently. We don't use services. All dependencies are lambdas that we actually inject from the outside. So this synchronized feedback, what it does is that it observes what task it needs to synchronize, and it just passes each of the values, and in case there is an error, it reports that it's in an error state. So this is pretty simple, and you can exchange easily, for example, implementation. Do you want to synchronize with some external service, or do you want to, I don't know, synchronize somewhere, wherever you choose. Or, for example, if you're in the unit test, you can choose how you want to define this, so you can probably do some kind of mock or something like that. So this is really awesome for unit testing. You can actually unit test on two different levels. So you can test the pure business logic, that's the reduce function and the state. Or if you want to test the composition with the effects, then you actually inject the effects in some system method that looks something like this. And that system definition just calls the implementation of that system operator in this case. Okay, the third part is the UI. So the UI is this. The view controller is, I don't know, 54, about 30 lines of code. And all that the view controller does is it creates a set of dummy tasks. This is probably a little ugly, but it's okay for demo purposes. And it just creates a dummy synchronized implementation that really doesn't do anything. It picks a random number, and if that random number is 0, in that case it will fail, and if it's different than 0, it will succeed. So it's pretty simple. You can imagine how you would mock something like this in your unit test. It's a bit ugly. You would, of course, create it here in the view control. What you would do is you would pass some lambda that is somehow injected into the view controller. Okay, so another thing is, how do you define UI feedback loop? That's the feedback loop that actually binds this to the screen, presents the alert, And that's here from 56 to 102. That's about 50 lines of code. It's nothing too big. It's pretty manageable. And that's it. Mostly here, there are some just dumb extensions, then concatenate the title, but nothing really too drastic. Okay, so let's assume that if I run the app, you'll notice if I run the app, notice how slow this thing works. So 1, 2, 3, 4. It's really extremely slow. Why is it slow? Because we are doing it one at a time. So let's say I would want to change this and make it work in parallel. What would I need to change? Well, I would need to change exactly one number and say that I don't take the first one, I would take, I don't know, 10 first ones. Okay, so let's run the app. There, it's a lot faster now. Okay, but we still have those flames somewhere. So what if we want to improve this and add some retry? Well, sure, we could do that. We could just add a retry here. I don't know, 3 times. One failed, but it's less. That one actually had a chance, but 1 in 27 to fail still. But we can add additional counters. We can add more sophisticated retry logics. But the point is that it's really simple to understand where you need to make the change, and the changes are simple, and you can really easily get really kind of sophisticated behaviors. A lot more complex than this toy example that I've just showed you here. So I'm not sure if I return the presentation, will I actually kill the recording again. So maybe I'll just, okay. So what are we doing right now? The basic concept is RxWidth. We have a lot of extensions inside the RxWidth community that actually enable you to hook up easily with any kind of state layer, with networking, with all of these effects for motions, etc. As far as for the architecture, this is my personal recommendation of the things that work well for us. They might not work well for you, maybe, but I have a pretty good feeling about this, and so far we didn't hit any dead ends. We are also planning to open source some of the solutions we've made. We'll create like a test generic OAuth implementation. We'll probably outsource the Bluetooth layer. There are already some paging examples, etc. So we are also doing kind of the other things. Like I said, I'm kind of responsible for the entire mobile architecture. So we also have an Android team. We are porting this to Kotlin. Basically, we've already ported this, but I still need to figure out how to actually post this on their package manager. And there are some concepts from RxWidth that we are using, like drivers, that we found really useful. So we are also porting this to Kotlin. There is no reason why this would work in the web environment, so we'll also, this is a micro operator, this isn't some huge library. So we'll just, try it out also on the web platform and see how it works with React, because React is basically only this kind of view layer. And we'll probably also open source some of the other kind of observable key value store that we were using, so you can have those state machines per key, etc. And that's it, basically. So if you have any questions.